Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to lecture 34, Organic Chemistry 2. Today we will continue on chapter 8, Carboxylic acid derivatives. We will cover the physical properties of carboxylic acid derivatives, interconversion of acid derivatives by nucleophilic acyl substitution. Let's start by the physical properties of carboxylic acid derivatives, the boiling point and melting point. Esters and acid chloride have boiling points near those of unbranched alkane with similar molecular weights. These acid derivatives contain highly polar carbonyl groups, but the polarity of the carbonyl group has only a small effect on their boiling points. If we look at the hexane, 1, 2, 3, 4, 5, 6, molecular weight 86, and the boiling point 69 degrees Celsius. When we look for the methyl propanoate, molecular weight very similar, 88, and again the boiling point is similar, 79. Propanyl chloride, molecular weight 92, and the boiling point 80. There is no much difference. On the other hand, carboxylic acids are strongly hydrogen bonded in liquid phase, resulting in elevated boiling points. The stable hydrogen bonded dimer has a higher effective molecular weight and boils at higher temperature. Nitriles also have higher boiling points. Here we have the acid dimer, molecular weight of 88. For the monomer, dimer is 176, and you can see the boiling point is high, 163. For the nitrile, similar molecular weight, 83, we find that the boiling point is high, 140. Remember that ester and acid chloride with molecular weight very close to the nitrile, 79.8 and 80 boiling point. Amides have surprisingly high boiling points and melting points compared with other compounds of similar molecular weight. In amide, we have these resonance structures. So when we have the primary amide and secondary amide, that this kind of dipole will increase the strength of the intermolecular hydrogen bonding. And in case of the tertiary amide, this dipole will form dipole-dipole interaction, intermolecular attraction in amide. If we compare isomeric amides, tertiary, secondary, and primary amide with the same molecular formula, C3H7NO, molecular weight of 73, we will see that in tertiary amide we have melting point minus 61. In secondary, it's higher, 28. Melting point of primary, higher, 79 degrees Celsius. So the melting point increases this way. In melting point, the tertiary is 153, secondary is 202, primary is 213 degrees Celsius. Again, the same trend. The primary is higher than secondary than tertiary. If we compare these to the acid Propanoic acid with 74 molecular weight, we will see that the melting point here is a little higher and the boiling point is lower than even the tertiary one. Solubility. Acid derivatives like esters, acid, chloride, anhydride, nitriles, and amides are soluble in common organic solvent like alcohol, ether, chlorinated hydrocarbons, and aromatic hydrocarbons. Acetonitrile, dimethylformamide, and dimethylacetamide with these structures are highly polar solvents that solvate ions almost as well as water, but without the reactivity of the OH and NH. We call them polar aprotic solvents. No hydrogen, no OH, no NH. These three solvents are miscible with water and often used in a mixture with water in chemical reactions. Interconversion of acid derivatives by nucleophilic acyl substitution. Nucleophilic acyl substitution are also called acyl transfer because they transfer the acyl group from the leaving group to the attacking nucleophile. The following is generalized addition-elimination mechanism for nucleophilic acyl substitution under basic condition. So the reaction starts actually by addition of nucleophile to the carbonyl with breaking the C double bond O. Then elimination of the leaving group, generating the C double bond O once again with the nucleophile on the carbon instead of the carbon leaving in the starting material. Again, this is addition, elimination, and called nucleophilic acyl substitution. As an example, the transesterification. We have here OR prime, ester, C double bond O. If we react with very small amount or alkoxide, OR double prime, in alcohol of the same alkoxide, addition will occur, followed by elimination to give the new ester. We call it transesterification. The reactivity of acid derivatives toward nucleophilic attack depends on the structure and the nature of attacking nucleophile and the leaving group. In general, reactivity follows this order. The more reactive is acid halide, acid chloride, then anhydride, ester, amide, and the carboxylate, the less reactive. Remember that Cl minus is less reactive. It will be stable. Anion, carboxylate follows it. Alkoxide, and the more reactive, so basic, will be the amide. In general, we can easily accomplish nucleophilic acyl substitution that convert the more reactive derivative to the least or the less reactive ones. So we can convert acid chloride to anhydride. Once again, we can convert more reactive to the less reactive. The other way around, it's like up the hill. You can do it. So, acid chloride reacts with acid to form the tetrahedral intermediate, followed by elimination of Cl. The Cl will deprotonate, proton transfer, to give acid anhydride. So acid chloride is more reactive than anhydride. Yes, this reaction can take place. So we start first step, nucleophilic addition, form tetrahedral intermediate, elimination, proton transfer, okay, conversion of an acid chloride to an ester. Acid chloride is more reactive than ester. Okay, let's see the reaction. Yes, the acid chlorides reacts readily with alcohols to give esters in a strongly exothermic reaction. This reaction requires caution, keeping the temperature low to avoid dehydration of alcohol, because acid chloride are powerful dehydrating agent. Pyridine also can use as a base to neutralize the medium, because the HCl is coming out of the reaction. So it neutralizes the media and make the reaction goes forward. Acid chloride with alcohol, nucleophilic attack, forming the tetrahedral intermediate, elimination, followed by proton transfer. And remember, we have here added pyridine to catch the HCl as pyridinium chloride, okay, and make the reaction goes forward. Conversion of acid chloride to an amide. This is much more stronger reactive than amide, so this reaction will take place. Acid chlorides react readily with ammonia and amines. The HCl generated by the reaction can protonated by some extra starting amine we add. So usually we add twofold excess of amine for this reaction, or we add pyridine or sodium hydroxide to neutralize the HCl. Okay, if you don't like to add more amine. So acid chloride with amine, first reaction again, step addition, nucleophilic addition, forming the tetrahedral intermediate, elimination, followed by proton transfer to furnish the amide. Conversion of acid anhydride to an ester. Which one is more reactive? Anhydride. Less reactive? Ester. So the reaction will take place. Okay. We have here acid anhydride. The acid anhydrides are not as reactive as acid chloride, but they are still activated toward nucleophilic acyl substitution. An anhydride reacts with alcohol to form an ester. Alcohol, first step, nucleophilic addition, forming tetrahedral intermediate, elimination reaction, followed by deprotonation, furnish the ester. Conversion of acid anhydride to amide. Which one is more reactive? Acid anhydride is more reactive than the amide. So the reaction will take place. Reaction of anhydride with ammonia gives primary amide. An anhydride reacts with primary amine to give secondary amide. Reaction with anhydride with secondary amine gives tertiary amide. So here we have the primary amine, nucleophilic addition, forming tetrahedral intermediate, elimination, deprotonation. We mentioned again, here is primary amine, and this is secondary amide. Okay? If we start this with NH3, we'll end up here with NH2, primary amide. If we have here NHR2, we will end up with NR2 on here. okay, and that is tertiary amide. In this case, we started with primary amine and we end up with secondary amide. Conversion of an ester to an amide, we call this aminolysis. Aminolysis means leaving the group by an amine, okay? Ester with amine, nucleophilic addition, tetrahedral intermediate, elimination, deprotonation furnishes the amide. If we start this with primary, we end up with secondary amide. Propose a mechanism for the reaction of aniline with acyl acetate to give acetanilide. What is a leaving group in your proposed mechanism? Would this be a suitable leaving group for an SN2 reaction? Acyl acetate with aniline nucleophilic addition, tetrahedral intermediate, elimination, followed by deprotonation to furnish acetanilide, secondary amide. And remember, here we have ethoxide leaving group. Would be suitable for leaving group in SN2 reaction. The leaving group is ethoxide, which is very strong base. It would never be a leaving group in SN2 reaction. In NS2 reaction, alkoxide leaves in slightly endothermic process. Here is the energy of the reactant, and here is the energy of product. It's endothermic process. The bond to alkoxide is largely broken in the transition state. In the acyl substitution, alkoxide leaves in exothermic reaction. Here is the intermediate 1 and here is the intermediate 2. The transition state 2, where the alkoxide start to break. So it's exothermic second step with the reactant-like transition state. The bond of alkoxide has just begun to break in the transition state. Which of the following proposed reaction would take place quickly under mild condition? Amide with sodium chloride to give sodium amide and acyl chloride. Which is more reactive? Of course, the acyl chloride is more reactive than acetamide, so this reaction will not take place. Acid chloride with methylamine to give amide. Well, acid chloride is more reactive than the amide. This reaction will take place. We have here an amide with alcohol to form an ester. Which one is more reactive? Of course, the ester is more reactive than the amide, so this reaction will not take place. Acid chloride with carboxylic acid to give anhydride. Acid chloride is more reactive than anhydride, so this reaction will take place. Anhydride with amine to give an amide. Of course, anhydride is more reactive than the amide, so this reaction will take place. Show how you would synthesize the following compounds from appropriate acyl chloride and nucleophile. Tertiary butyl acetate, tertiary butyl acetate. So retrosynthesis, we will get this compound. This is the carbonyl, and this is the substituent. Oh, what we will do, we will cut in here So that will be acyl chloride and alcohol. So you react acid chloride with tertiary butanol in presence of benzene like dimethyl aniline or pyridine in ether and heat furnishes the ester. Once again, we use the base in here to catch up the HCl generated from the reaction and get the reaction forward. The reaction condition is published in 1944 in Organic Synthesis. Cyclohexane carboxamide, that cyclohexane carboxamide in here. Okay, so what we do is cutting between the carbonyl and the leaving group found to be ammonia. So it is the acid chloride and the ammonia together furnishes the amide straightforward reaction. See you next lecture.